Hello, my physics friends. We just figured out the rotational inertia or the moment of inertia for a long thin rod. If the axis is at one end, it was 1/3 ml squared. And I mentioned that you could apply the parallel axis theorem, which is I equals I naught plus mh squared, where I naught is the moment of inertia about the center of mass, which is the calculation we're about to just do. And h would be how far your axis is from the center of mass. So that's a derivation or an example we've already done, but let's revisit this. So we've got our long thin rod, definitely the same as a meter stick, but instead of the axis of rotation being at the end, it'll be in the center. Remember, in order to perform the calculation for the moment of inertia or rotational inertia, you don't actually have to think about torques or angular momentum. You can consider it just based on the geometry. So the most important thing is where is the axis of rotation. So in the last example, it was on the left end. This is still going to be the x-axis. This is still x plus x, so this is still 0. And this point down here is still L, so none of that's changed. Lambda, the linear mass density, is still m over L, which means that, well, that's not a thing, which means that lambda dx is still equal to dm. So what we had said is if you take a thin little sliver of your rod, might as well think of it as a meter stick, and this thing has dimension dx, then it's got mass dm. And if we can imagine this little orange sliver moving to one end or the other, what we're really trying to do is sum up. It's the integral of all of the r squareds times dm's. The trick, though, is that r doesn't make any sense for the context we have here. It's really, for us, the integral of x squared dm. So that's very common for College Board to do. They'll use r to refer to a distance measurement without necessarily locking you into an axis. But in this case, we've taken our long thin rod, our meter stick, and we've put it along the x-axis. So instead of r squared, it's x squared. So that's all the same. So nothing's changed. So what we did is I equals the integral of x squared dm, but we replaced dm with lambda dx. So that was the integral of x squared times lambda dx. Everything is the same. Lambda times integral of x squared dx, except the limits. Last time we integrated from 0, because the pivot was on the far left, all the way to L. Here we're going to go from negative L over 2 on the left-hand side. Oh, I guess maybe it's not 0 to L. I should be careful. We're going to make our origin right here. This is 0. This is negative L over 2. This is plus L over 2. So I apologize for marking my axis wrong. I need to measure from the axis of rotation. So that little orange sliver would have a negative distance away from the axis of rotation. If I had another orange sliver over here, same size, same mass, so it's also thickness dx. So that's the same. And it still has dm. But this has some positive distance away from the axis of rotation. So we're going to go from negative L over 2 to plus L over 2. So the integral, by the way, does not change. So I equals lambda times quantity 1/3 x cubed. And our limits are from negative L over 2 on the left to L over 2 on the right. So how does that change things? So I'm going to factor the 1/3 out, and then we'll have L over 2 cubed minus negative L over 2 cubed. That's a cubed, by the way, like that, which means that didn't get much better. Still looks messed up. So let's go ahead and simplify or carry out let's do some math. L over 2 cubed would be L cubed over 8. And then negative L over 2 cubed is, so think about it this way. We could take the -1 and cube that, and that's a -1, times the -1 right here, and you get positive. So we end up with this L cubed over 8 plus L cubed over 8. which is the same as, remember, this is the rotational inertia, and now we could even say that this is I0, I naught, since we're specifically talking about the center of mass being our axis. So this is I naught, which is the one we referred to in the parallel axis theorem. So let's keep going. Lambda over 3 times quantity, L cubed over 8 plus L cubed over 8 is 2L cubed over 8, which is L cubed over 4. This is a lambda. My penmanship is poor. There we go. I don't know if that's better or not. So now I've got this 1/12 lambda L cubed. All right, so because 1/3 times 1/4 is 1/12. So let's keep going. I naught equals 1/12. And then lambda is mass divided by the total length times L cubed. One of the L's cancels, you get L squared. And we get 1/12 M L squared. So I naught equals 1/12 M L squared. Now, if we use the parallel axis theorem, I equals I naught plus M H squared. In order to figure out the moment of inertia or the rotational inertia, if the axis is moved to the far left end, then the H would be L over 2. So that would be 1/12 M L squared for I naught plus M L over 2 squared. So that's L squared over 4. So we factor out the ML squared, and you have 1/12 plus 1/4. And I'll let you prove this to yourself, but a 12 plus a fourth is a third. So you end up with the 1/3 ML squared. So you can find the rotational inertia of a rod about its far left end by using the parallel axis theorem, or you can use calculus like we did in the last video, but they both will get you to the right place. And by the way, 1/12 ml squared is the rotational inertia of a meter stick or a long thin rod if the axis of rotation is through the center of mass, or what we would think of as I naught. Okay, we're done with that one.